So as I told you in the end of the last lecture, we finished covering the material that I want to give in this course, and I'll divide this the last lecture into two parts. One part is connected with the clips that I have done, so if you have questions about it, I'll be happy to answer. One of them I've already heard, and it's a good point to start a general discussion on what's going on. And the second part, I'll say a few words about the exam, describe, actually demonstrate how I construct a question, so you'll get some feeling what is happening regarding to questions in the exam, but you have questions if you have your own. Okay, so the clips that, the short videos that I've put on YouTube was to whet your appetite about the questions of quantum mechanics. Basically, we have quantum mechanics on the one hand, as I emphasize, is a very clear mathematically constructed field. Tell me what is the Hilbert space, tell me the Hamiltonian that governs the dynamics, and I'm able to tell you what is the probability at any given time to measure any given physical quantity. It has some mathematical background, but that's it. Then you have the second point, which is measurement. And measurement is actually not within the descriptions that we worked until now. What do I mean? Well, you construct a probability, see how it develops with time, and when you perform a measurement, you actually know the result. And at the moment you know the result, all your previous knowledge is somehow wiped out. And you are unable to answer what you will measure. All you can do is say the probability. And basically, once you measured one property, it's not necessarily that you can say something about another property. As we have learned, if you measure one property, what is the requirement that you will be able to answer questions regarding to another property? The commutation relation. If they commute, the operators that represent the physical quantity commute, meaning they have the same eigenvector, So if you measure the system in one eigenvector, you know both physical properties, and you can straightforward answer these questions. If not, you don't know what will happen with the other property. And this is basically the point that breaks up our classical intuition. If you say, well, quantum mechanics is only a theory of probability, it's not correct, because it has more relations built into it. And this is actually the whole point with the Bell inequalities. That's the first demonstration that indeed this is a situation, and it can actually be proven mathematically. Just take it a moment.
לא עושים באלקטרוניקה. מה קרה שמונה?
אין לנו כלום, אחי, אני לא יודע, כאילו, אפשר להעתיק משם, אבל זה גם, זה להעתיק אחד לאחד, מה, כאילו, אם הוא רואה את זה, מה הוא פשוט יגיד לך.
Okay, so what is the main idea behind Bell inequality, which also has to do with the new concepts that became very popular in the last few years, entanglement and quantum computation. The main idea is basically I have to say something about a system that has more than one particle. All these concepts of Bell inequality, entanglement, both of them I'll illustrate here, and quantum computing, which I won't illustrate today, but it's built on the same ideas, is that we can know something about one of the particles if we measure the second particle. Okay, so first of all, you can stop me and say, well, it's not clear to us what we are talking about here. We have, until this point, described the theory, quantum theory, of a single particle. What does it mean to have a quantum theory of more than one particle? So, there are 2 points that are connected with describing more than one particle. One of them is easy, and I'll describe it here. The second is more intricate, and you'll actually learn about it only in advanced quantum mechanics as a graduate course. Okay, and what is the difference between those 2 descriptions? It's are the particles identical or not? Because if I have 2 particles that are not identical, it's almost trivial to write down what is the quantum mechanics of such a system. If they are identical, it's more problematic, and I'll try to explain why.
Not trivial to be different, because if they similar, they will act similar.
Okay, so you pull me into the system. Okay, let me describe easily what happens. Let's say I'm starting an experiment with a particle here and a particle here. Now, in classical mechanics, what do? You write down the x and p of this one, x and p of this one,
and get all the
forces,
yes.
And you calculate what is the probability of seeing this particle at a different point. Sorry, not problem. Where will you find the first particle and where will you find the second particle, right? Now, if they are not identical, the question is easy. Why? Because if they are not identical, if I'm looking at the particle here, I know it's the first particle or the second particle. This guy was a purple particle and it had such a trajectory, and then I saw it here. And this particle was a red particle. It started here and went to here. Okay?
I can identify it.
I can identify. It's meaningful to ask where. If they're identical, so let's assume that both of them are red. How do I know that this particle ended up here while this particle ended up? what should I do? Instead of looking at the picture only in the end, which was enough for the case that they are not identical, I'm taking a picture every split second, and I'm seeing that this moves here, this moves here, this moves here, so I can trace a trajectory and tell you this particle ended up here, and this particle ended up here. On the other hand, for quantum mechanics, I can't do it because each time that I'm taking a picture, I'm changing the conditions. So if I take at the end a measurement and I have a particle here and I have a particle here, there are two different configurations that look the same to me. And mathematically handling these two different descriptions that can occur requires a more complicated mathematical structure, and in the end of the day, that's the reason that it manifests itself in two different behaviors, fermions and bosons.
That description is with the Fock space, right?
And it's known as Fock space, which is actually a Hilbert space but built up in a certain way. So that's why these similar particles are easier, because then I don't have to worry. I know that if I can tell you the probability for finding the purple one here and the red one here is well defined. So let me start with how do I think about quantum mechanics if you're set up with a problem that you haven't seen before. What do we know actually about quantum mechanics?
It's linear theory.
Okay. Of what?
Wave function.
You're in the direction, but why to be so specific?
Of any
vectors.
Of a Hilbert space. First thing you have to stop and think, what is my Hilbert space? Once I know what is my Hilbert space, I'm already made a lot of progress towards describing the quantum mechanics of the system. So let's start from a very, I guess it's the simplest many particle systems that I can think about. Two spins, and why spin? Because it has the lovely properties that for one spin I have only two states. So it's as simple as you can be without being totally trivial, because if you have only one state, you have nothing to say about it, except it's in the state finished. And if you think about it, I'll pull you out to something of a paradox. Some of you perhaps heard about quantum theory of the whole universe.
theory of the whole universe.
I want to write
Cosmology, right?
cosmology. I want to write a quantum theory of the whole universe.
A wave function of the universe.
A wave function of the universe. If you stop a minute to think about the statement, it's completely trivial. Why? If I'm at a state, and I can't say nothing about it. I can say it's in this, and I have nothing more to say about it. How it develops in time, as long as it's in an eigenstate of the Hamiltonian of the whole universe, it's there, it accumulates phase, but it does. right? So then you can stop me and say, but that's not what they are asking. Because they're asking about a probability of measurement of the wave function at a given spot, at a given area. And there, a wave function can have different probabilities to measure things. But if you think on the global scale, it has no information. It's in a state and it's there. Okay, who cares?
But it's composed about little wave functions which they change.
Then you have to go and start to talk how you write a quantum mechanic theory of part of your system. And that's a density matrix. We didn't touch it at all. It's an important topic, but it appears in more advanced, because let's say our basic notion that the particle has to be there doesn't exist if you're looking only on part of the system. If you're looking on a part of the system, it may be here, it may be not here. It can have a probability anywhere between 0 and 1. Okay, so we have a wave. So for one spin, my Hilbert space is simple. Put it this way. I have two states. That's all I have. And ask about it. Questions, let's say, what is the z component? What is the x component? I can't ask what is L squared because it's trivial. Well, I can ask, but the answer is trivial. Okay, let's assume that we have two particles. Second particle, same thing, could be up, could be down. And I'm writing it down in different colors because they're distinguishable. I can ask you, is the first particle in up and the second particle in down, and not vice versa? It's not the same situation because I can't separate the two particles. If I can't, you see that saying that a particle, one of them is up and one of them is down, is a meaningful statement. Saying the first is up and the second is down has no meaning, because I can't answer you who's the first and who's the second. Okay, so so the size of the Hilbert space of this guy is 2. The size dimension of the Hilbert space of the second one is 2.
Not in our example, but they can be different. No.
Well, I could come and tell you I have a spin half and a spin 1 particle, and one of them can be at up and down, and the other one could be 1, 0, and -1.
Then n1 is 2 and n2
is 3.
Yes.
Right? So, for the global system, when I'm looking on the system of the two spins as a system that I'm addressing my questions on this system, what is the size of the Hilbert space? Or I have to say something about the first particle. Is it here or here? And the second one, is it here or here? So I have to write down 4 states. Then I can be very mathematical and say that I'm doing an outer product of those two vectors. I could use just simple physical intuition and say, look, what do I want to describe? Let's call the first number state 1 of the first spin and 2 of the second. I can be up, I could be up, down, I could be down, up, and I could be down, down. Have four states, that's my Hilbert state of the system. That I use on the system will have to correspond to this structure of the Hilbert space. Now, I could ask simple questions, I could ask more complicated questions. Let's take a simple question. What is Lz of the first particle?
In the second part.
Well, I don't want to say the words tensor because it's correct, but I don't need it here. It's more complicated than I really need. Okay, what do I do with an operator? I operate it on my wave functions, right?
זה תן לה בכיוון זה.
כי זה אליקס של
הוא עושה
y,
אפ.
כי זה אליקס של y. קומוטיישן של אליקס של y.
כן. מה הוא עושה עם אפ? הוא מטיל אותו. עכשיו נבדוק.
Okay, so what do I know about this guy? Oh, simple. What is the state of the first one? Half, I know. Let's add the H bar. And without any manipulation, I know it's an eigenfunction. Okay, this is still up.
Change the order of the arrows there.
And put mine.
You have to write it correctly because that's identical to it. Okay. So, even for the many particle Hilbert space, these bases are the bases of eigenfunctions of LZ1. What? Approved. It's also the eigenfunction of LZ2. Now I can show a nice thing. Okay, this is a one particle operator, right? I want to find angular momentum in the z direction of this system. Okay. What will be the most natural definition of it? Would be Lz of the first particle plus Lz of the second particle. What else could it be?
Lx and Ly commutation. Ah, only with this?
I want to know what's Lz. Why to stick my head into a problem? Did anyone ask me about X and Y? No, I asked what's Lz.
Just sum altogether.
L1 of Z, Lz of 2. The same if I want to do the total momentum of a system of particles. This is the momentum of the first, second, third, and so on. And my life becomes more complicated because who is the first, who is the second, who is the third for identical particles is not well defined. And that drives you into all these problems. But as long as I can tell you who is the first, who is the second, who is the third, let's say I have 5 particles with different masses, each one of them. I ask what is the total momentum. No problem. Momentum is the first, second, third, and I know what is the first, second, and third. They have different masses. Okay, so then actually I can answer this question. What is Lz of the up state? One for this guy, one for this guy. H bar up. What's the order I did it? This way.
0.
Half minus half. For the same reasons. Okay, so it's also an eigenfunction. Eigenvalues and eigenfunctions of Lz are described by this basis. Okay, here is something very interesting that anyone who did atomic immediately identifies and is connected to things that we did in the previous lecture, but didn't explicitly say anything about it. What do I have here? Okay, I have here, let's write just in general, 0, 0, 1, 0, 0, minus 1. Now, when I take 2 spins half and look on their combination of angular momentum, what do I expect?
Single energy level?
If in classical physics, I would tell you you have 2 spin half systems, 2 vectors of size half, and I combine them. How should they behave? Maximum as something of spin 1. Let's look what we have. We have 1, 0, 0, minus 1. The 1 and minus 1 I understand, because that's exactly the behavior you expect from a spin 1 particle. One of the zeros I would have bought immediately, okay? Whole numbers. But why do I have here 2?
Interference, right?
No, much, even simpler.
We have two particles, so we have 0.
Classically, two vectors size half, you can have any value between 1 and -1 in any angle, right? Depends on what is the vector of the. Quantum mechanically, if you add two particles of spin half, you have either they behave like a particle of spin 1 with 1, 0, -1, or a particle of spin 0. What is the possibilities of LZ for spin 0?
Just 0.
Just 0. That's the second 0 here. Now life becomes a bit more intricate because the ones that belongs to spin half is sorry, the ones that belongs to spin 1, the zeros that belongs to spin 1, and the zeros that belongs to spin 0 are both linear combinations of these guys. People who are doing atomic physics knows that you have a triplet, 3 states that belong to spin 1, and a singlet for the spin 0. And all this you got from basically counting on the levels that you could have done with bright third year elementary school kid. I didn't put in here almost anything heavy, and you get a very basic result just from looking on the Hilbert space. So basically, now you know how to construct a many-particle Hilbert space for non-identical particles, and you can ask yourself questions. Now, what goes into Bell inequality? Bell inequality forces you to take this Hilbert space seriously. What do I mean by seriously? So everything there goes on a case that you have two particles. Putting them at the same point. You had one particle, let's say a singlet, meaning the total spin and LZ was 0. And you sent one of them, they were identical, but you send one of them here and one of them here, and you have two experimentalists, one sitting here and the second sitting here. Once I said you send two of them, one here and one there, they're distinguishable because I can say I'm measuring the property of the particles that went left, and I can say I'm measuring the property of the particle moving right. They're not the same, they have the same mass and whatever, but they're at two different points. So I can already distinguish. So it makes life easier. Now, classical physics, okay, I was at a state with LZ, total LZ equals 0. Quantum mechanically, it tells me that I'm either in this state or in that state. Can't be in both of them up, can't be in both of them down. And telling you that it's the superposition. The minus belongs there, but it doesn't make any difference. Now, what it tells you, and that's totally understandable on classical terms, well, you measure this one up, this one has to be down, and vice versa. So you can stop and say, oh, that's very interesting, because until I measured it, I didn't know which one is what. Once I measure it, I know what the other one is. But the truth is, it's not interesting at all. Why? I could look on a classical case. Let's say I have a red and a black one. I don't know which one goes in which direction. So I write a probability half that the blue one is the red one goes in this direction and the black one in the other. But that's a fixed probability.
But that's different in quantum mechanics, right?
Just a moment. That was the last 2 or 3 clips in this video series. So it's like I give you a bag with a black and white marble, pull out a marble, I look at the bag, I know what's the marble that you pulled out. Oh, very, very amazing. Loud round of applause for this discovery. It's trivial. So how do I differentiate between quantum results and classical results? That was the whole video that I gave. And that comes on the point of view that I don't measure the same things at the 2 experiments. So what do I mean? One of them, for simplicity, will continue to measure in the z and minus z direction. But the other one will decide on some angle. We'll measure it, let's say, in the x plus z direction. And that entails that the 2 particles, if quantum mechanics is not true, if you have a hidden variables somewhere beneath the behavior that we see, there's a deeper reality. Then those 2 particles, at the moment they left this point, should have a table that tells each one of them, okay, if you are measured up and you are measured in some angle, you will give this result and you will give this result. And in principle, you could have constructed such infinite table because you have the freedom of measuring whatever angle you want. But such table has constraints, as I have explained in the videos, on what is the correlation between the 2 cases. Some combination of the operator z plus x, and you'll get the result. It turns out that the probabilities of measuring something in that way are higher than is possible in classical probability. And that's what's measured in experiment, and therefore quantum mechanics is correct, and any local hidden variable is wrong. So why do I say local? Because if they're exchanging tables once they're at the 2 different points, it's non-local, but then you can fix up the probabilities and correct them, meaning you don't have a fixed table, you have a table that depends on what measurement is secondary. There's another way to correct it, which I don't understand at all, but some people find it very appealing. Name superdeterminism, and that tells you that the experimentalists didn't have a freedom of choosing at what angles the measurement occurred. To me, this is much more problematic than any acceptance of quantum mechanics. So what does this whole Bell inequality tell you? That the basic playing field where everything happens is the playing field on the level of the Hilbert space.
And also you can explain it with many world interpretation.
Oh, many world doesn't.
They say that every possibility did happen, right?
Yeah, but many world is an answer and is not an answer. Why do I say it? Many world, you don't need two particles for it. What many world wants to answer is the problem that we started with. What was the problem that we started with? Wave function collapse, which is not described within quantum mechanics, right? So that's bad. You don't want a theory that part of its dynamics is here a miracle happens, you measured this and that was the result. Or in a mathematical language, you add a linear evolution and suddenly you have a non-linear evolution on a very short time that told you I measured this guy that I even can't write down the equations of it. I can't determine anything. So that's problematic. Many worlds interpretation tells you the following. You think that there is a collapse for the simple reason that you treated two parts of the system differently. What do you mean?
You see something is classic.
I had my spin, let's say, that I could measure up and down, and I had my measuring device that is not described by quantum mechanics. That you're not allowed. You're building here a theory that describes part of the system and not the other part of the system.
I have to assume that the measure it's also a quantum.
So let's go to our good old, once I have two parts of the system, I need many particles. That's one of the reasons that all the nice things of entanglement, quantum computing, and so on happen with more than one particle, because there really quantum mechanics shines, shows its different behavior. So what's a measurement in this case? Let's call red the measuring device and black the system that I'm measuring. Okay. And let's start, let's say, from a state like this. Why not? Then I say, well, the red guy is the measuring device for the black guy. So if the first guy was up, the measuring device will be down, and as an experimentalist, I would be able to tell you, oh, the black guy is up, or vice versa. If the red guy will be up, I'll tell you I measured that the black guy is down. Great. So, and this is my wave function. So the classical description would be, okay, I measured on the red guy up. This part went to hell. This guy became 1 because that I measured, and that's the collapse of the wave function. I ended up here. Many world interpretation tells you, no, why do you come and complicate the story? This is a wave function, and it remains the wave function before or after the measurement. But what is the measurement? In one branch of the universe, you see this state. In another one, you see this state. Both of them exist, but you insist that you're seeing this part. Now, for me, it doesn't help much because you moved the ambiguity a step forward. What do you mean? Well, I'm here and I see the result of the measurement. Well, I can't deny that I'm only a simulation. I don't know what I'm seeing. Everything is hallucinations. That's fine, but that's not a very useful point to describe reality if you believe there is reality. You can argue on that. But I see this part. Why do I see this part? What the term, well, you can answer me, well, no problem. There is a version of you seeing this one and a version of you seeing that one. At the end of the day, I see one state, so why not go back a step and say that for me the wave function collapsed. Some people find that better, but from the point of view of shut up and calculate, it's the same thing. You can tell yourself whatever story happened, but if you measured this one up, you saw this one down, and the probability of continuing doing something is either that it collapsed and this is the branch that you're in, that's the only thing that remains, or there is another branch that you can't access, and for you that's the only branch that remains, and you still can't do anything with the other part. So that's the difference between many worlds. Now, Hollywood, of course, took this concept and made a lot of movies about your switching between different different branches of the wave function, but that has no reality in the description. Okay, so now the details of what I said, why the probability is higher for quantum than in classical. You have a detailed calculation in the clips. So if you're interested, see, and that is the basic strangeness of quantum mechanics. Now, what is entanglement? Entanglement is exactly the statement that if I measure one of these particles,
the other one is completely determined.
It doesn't have to be completely, has a higher probability of being able to predict something about the other particle. Although this guy, this experimentalist could sit on the moon, this guy on Earth, you separate them. They are doing it nowadays, sending from such an entangled pair, which, when they say entangled, basically mapped up to this state. And they're taking two photons, sending it, I think it's a Chinese experiment, from a satellite that creates two photons that are entangled. One is sent to a station in Beijing, one is sent to, I think, in Vienna, in Europe somewhere. And they're sitting measuring, they don't have even time to coordinate the measurements because they're too far ahead, and they're logging, and each time that this guy sees the photon up, he sees the second one sees the photon down, and vice versa. Now, you can say, oh, I opened a communication channel. Because this guy saw up, this guy saw down, so there's correlation. But I can't use it for communication because it's totally random what I'll see. So you can't pass information that way. You only can afterwards meet and say, oh, let's check my logbook, let's check your logbook. Works perfectly.
And that's why it's not, it's Lorentz invariant, right?
Right. It doesn't have any contradiction with relativity because they can't use it for communication. You can use it for security because of this complicated structure. Let's say if someone sits here and detects the photon, measures it up or down, you perform the measurement here, so you change the wave function. And you have a set of protocols that you can measure and decide if this really happened or it went directly to here. So that's what's called secure key distribution. Because that you can pass and check that no one on the way eavesdropped and copied your message. Because you can't reconstruct a wave function of 3 particles that will have exactly the same statistical property. Why I need 3? Because I swallowed one and I'm sending a new one. And that I can't hide that I swallowed one. In classic eavesdropping, yes, I'll hear, write down the signal and send the same signal. And if I do it quick enough, no one will be able to detect that delay, and it's fine. But in quantum mechanics, once I measure, I change the property, I collapse my wave function, and to create a new wave function that looks exactly like the previous one, there's something that's known as a non-cloning statement in quantum physics. I never can exactly
that's why you cannot copy-paste in quantum computers, right?
Right, because, and that comes from the simple reason. I increased the number of particles by 2, I have a Hilbert space by 4. It's actually, if I have L particles, it's 2 to the power L states in the many particle physics. That's one of the problems of doing quantum many particle physics. It's just becoming a very huge Hilbert or Fock space for who wants to be a bit more precise. But this huge exponentially increase in your Hilbert space means that you have to provide an amplitude for each possibility. Just too big. Can't do it.
I understand why if we measure in the rectangle, we see there is a different wave function. But how I know when I get the signal that he changed the wave function in the way?
So I send a few signals. One of them I use for my key distribution, the other just for statistical analysis. And then I start measuring in all kinds of directions, not only Z, of X plus Z and all kinds of directions. And if it was collapsed here, I will get a different statistics than if I didn't have a collapse here. So I send more information, use part of it to detect that no measurement was performed, and the other part to distribute my key. Because once I know that here I have 1 and here I have 0, I can have a protocol to build a It's occupation key for measurement. And no one else can know it, because if he knew it, I know that he knew it and I stopped using it. So this is in one-shot entanglement and quantum security, what's called. And quantum computing is basically taking, so you see that your Hilbert space grows in an exponentially power for each
any particle. Yes.
Any particles that I add, any qubits that I add, a particle is a qubit. And if I build up all kinds of initial states and by some manipulation of operators, that's the gates there. I just apply, I get a certain wave function or a certain measurement if it's true and another certain, if it's wrong as a result. Do I have this string within it or not? Well, what the big problem with quantum computing is, what do you want to do with it? Okay, I have a set of quantum bits. What can I do with it? I can set an initial state and then see how it develops in time, and I can control the development of time with gates. What do I mean gate? It's just applying a different Hamiltonian for each state. So I started with some wave function, ended up with some wave function, and then I perform a measurement asking, for example, are the two first qubits in an up state? If yes, it tells me something. If no, it tells me something else. Because that's quantum computing at the end of the day. Now, what do you need as an algorithm? You need something that will give you answers what will be the end measurements after I'm doing a set of manipulation.
After all the gates and
I set up my problem, some wave function, a state on these quantum qubits. I do some operations, which is just applying Hamiltonian to see the progress in time, and then I perform a measurement. That's all I can do in quantum computing. I don't have other games to do.
It's also in regular computing. You just get the beats and
do things on it.
Things with it. Yeah.
The big problem is we have a whole library of algorithms to do things in classical computing. We have very few algorithms that work in quantum. Basically, it's factoring primes, doing a search, and
but every algorithm quantumly is way more faster.
No, this extremely small subset of algorithms which is factorizing and search. And search is not so good.
They don't do it way faster.
So Shor's algorithm is exponentially faster. That's the only thing, as far as I know, that is really much better.
Shor means just
Shor is a person that Schor. The name of the person who came up with this algorithm 40 years ago.
Also, the Fourier transform is more natural.
Yeah, but let's say search is just polynomial faster, and polynomial, you pay a huge price to set it up on a quantum computer, and polynomial is not worth, a polynomial speed up is not worth it. So At the end of the day, at the moment, the only guys who are really, really interested is anyone who wants to break the encryption that you have today on the internet, which is based on factorializing primes. Everything else at the moment is not worth the effort. So why they are continuing with the effort? Well, perhaps they'll come up with such algorithm. And let's say from the point of view of physics, no, it's more than interesting. Actually, you can, well, that's almost a cyclic explanation. I can use quantum computers to simulate quantum systems, because that's the most natural thing to do. And simulating quantum systems on a classical computer is a pain in the neck, because what you do in a classical computer, you exactly do what's here and here. You write down the Hilbert space, you write down matrices which are the operators, you diagonalize the matrix, and you get the results, what's measured with what probability. You can see if it grows up like to the power of L, once I have here something like 100, 16 or 18 is a stretch. You are out of the game. So still, qubits you can nowadays get 100, 150. So it's to the power 80 more larger size of a Hilbert space you can approach. It's meaningful. Well, there are for certain systems all kinds of ways to do approximations, but that's what you have in this thing. Okay, so that's about quantum mechanics, general philosophy, a bit of a taste of what you have in many body physics and entanglement and quantum computing. What I'll do after the break is basically show you an example or two of how I construct a question for the exam, just so you'll get a feeling how you should prepare yourself for it. So what I'm going to do in the remaining hour or so is give you a taste on how I'm creating an exam. Hopefully it will help you to study towards the exam. So actually it starts from a question that I don't know if you as students ask yourself, but if anyone of you will continue to be a faculty or a teacher somewhere, comes to the question, what is the purpose of the exam? And you'll immediately throw at me the usual answer, is to check whether you have learned the material that should have passed in the course, right? Or just to torture you, I don't think is, at least you can't give it as an official reason for an exam. So from where do you take an exam? At very basic levels like arithmetic or whatever, you have infinite possibilities to compose questions. Life is good for you, at least for you as a lecturer. Once you get into more complicated material, questions that are solvable in a finite amount of time become rarer. So you have two types of solutions, probably have more types of solutions, how to choose a question. One of them, go over all exams that were given here or other places, make small adjustments and give as an exam. I very much dislike this way of writing down an exam. For the main reason is that, actually two reasons. One, it benefits people who sat down and did an infinite number of examples, which I don't think is the best way of learning. It's a good way to learn how to pass an exam. It's not the best way to understand the material. Well, second is that nowadays, when you have internet, ChatGPT and things like that, you can immediately ask, give me an example of questions in XYZ. You get some finite number of questions, and if you pull out the question for there, it just benefits people who did this type of research. And I'm not so sure that is the goal of the exam. And third, I don't. It's a derivative of both. It doesn't really probe your understanding of the course, because the goal of the course is that you will have a good grasp on the basic ideas of quantum mechanics. Sometimes some mathematics also come into play, but that's the main. Okay, so what I do is usually I sit down and try to come up with a new question. Of course, you have some pathways in your head, and you sometimes go to similar type of questions, but I try to avoid it, not always at once. So I'll give you an example, and I'll do it live. I'll try to construct a question and see what happens. Therefore, I can't tell you immediately that there will be 4 questions with 2 subsections each, because I don't know. I haven't sat down, I haven't written down, so I sometimes start and end up with 2 large questions or 3 medium ones. It depends how it goes. Sometimes I write 3 medium ones and it decides that one of them is no good and I have to expand the other 2 or something. It depends. So there will be between 2 and 3 questions, with each one with some subsections, and you'll get the number of points for each subsection. But during the exam, you can decide how much time to spend on each subsection. Okay, so sit down and let's say, since we did the last hour things that are connected to angular momentum, let's try to build a question on angular momentum. Okay, what do we already know about angular momentum? Well, we know the Hilbert space. It goes back to the same, and I want to emphasize all the time that the basic concept. Understand what is a Hilbert space, write down the operators, find eigenvectors, find eigenfunctions, and understand how this is connected to probability. That's, in the end of the day, the games that we are playing here continuously for different types of questions. So I'm sitting for a moment and saying, well, we know these are my basic ingredients. I know that this guy is an eigenfunction of this guy and of this guy. And let's see what we can ask you in order to check if you understand it also. Now, one thing that I don't want to do, okay, if I write down explicitly phi is a simple exponent, not too problematic. I don't want to get into too heavy mathematics with Legendre polynomials. Just don't want to go there. But you will have problems, I'll have problems checking it. Someone did a mistake with a minus somewhere, and I have to dig through 3 pages to understand where did he understand what he's doing? He just made a small switch with mistake, or did he do something completely illogical? Because sometimes a small mistake in the beginning could lead to something. And then you have the second question when you're checking it. Well, should he have noticed that he made the mistake? Sometimes it has to come up immediately. Let's say if you calculate an expectation value and get an imaginary part, I very much can give 3/4 of the point for someone who ended up with an imaginary part. And, oh, this is stupid, I can't find my mistake. For me, it's much better than someone who leaves it and is happy with this. Okay, so I have these guys and I want to ask something. Okay, usually, not always, you want to write some Hamiltonian. The whole game goes on some Hamiltonians. So let's start from the simplest Hamiltonian, L square. Is this a Hamiltonian? No. Why? It has not units of energy. So I could be lazy and just write here A and write units of energy divided by h bar square, but I must say it's not very nice. So you go and write I, and then you stop and you say, what is this I? This is inertial momentum. Why do I know it? Because L is so units of r square, units of p square. And the inertial moment is m somehow r square, and p, and if I lose this, p square over m is units of energy. That's fine. You'll be amazed that 10 or 15% of the students will get stuck here with this I. We don't understand what is this I, from where it comes, and if you even write inertial momentum and you have open materials, I'll start to read the whole book to find what it means, and it's completely a waste of time. Okay, so if I just put this guy as a Hamiltonian, I could decide that I want to bump up the average and give 5 or 10% for just writing the eigenvalues and eigenvectors, meaning
you can be also in another. You can use another logic, right? You can say that the L is analogous of momentum in rotations, therefore I must be the analogous of mass.
That is very true. And the eigenvectors are and I would bet that a quarter will write down just L square and won't understand what's wrong with it. Okay, but that checks something. Now I want to make it a bit more interesting. So I'll add a term. So I don't want to make it unsolvable or needing heavy mathematics. Okay. What would be the easiest way to change the Hamiltonian, but not complicate the calculation?
You could add the angular momentum on the z-axis, but as if there is an effect.
Exactly. So first of all, adding LZ, it commutes with L squared, leaves you in the same eigenvalues. Life is good, except I have to add here a magnetic term for units at the moment. Then I can, so I'll put here something with the correct units and I get, now I can, but that in some sense, whoever went through this, I expect will also go through this. So what I'll do to check if you really understand what happens here, I'll try to hide my hand. Write it down, but so if you don't understand, you won't be able to see immediately what it is. Let's say I write this is just the constants, this is magnetic moment, this is a G factor, it's just a number, but in general terms it appears here. And B could be a vector, right? As we said about the measurement, it's not superdeterminism. B could be in any direction that I switch my magnetic field on. So I'll write down this term. Without changing the physics, I made the question something that probes more understanding. Why? Because one thing you should have been exercised till death to understand that if you have a multiplication of two vectors, you have all components of it. So what's really written here?
Just BZ.
No, actually, what it's another. You're right that this. That's what's written. And this is a headache. Here comes physics, which you said. Well, I'm free to choose directions. I'll decide that the direction that I choose is B. That's completely within your prerogative.
Testing test, we have to understand the law. We need to.
I will write down something. That's what I said. The first section is the trivial one, just giving points to anyone who has a basic understanding. Here, I want to check if you you have a basic understanding of physics. This is not yet quantum mechanics.
Yes.
This is just something that should be, as a physics student, extremely ingrained in you, that choosing your axis is your prerogative. It's not something that comes from the sky. And if someone insists on, I could even tell you B is Bx, By, Bz, and you can tell me, but I have that depends. If I want to make it even harder, I'll say here B is Bx, By, Bz, and you'll tell me, who cares that you call it Bx, By, Bz? I can transform it into an axis where it's Bz.
As long as the magnetic field is constant, right?
I don't have constant in what? In time, I didn't put
Space.
in.
No, in space.
But I don't have space here.
But if it's a function, you cannot write it like that.
If it's a function of x, y, z, so I'm missing here the x, y, z components, right? My Hilbert space just refers to theta and phi. I'm looking on a spin, which is somewhere, and my questions are, what are the theta and phi, right? In classical terms. Okay, so I expect and what are the eigenvalues and eigenfunctions?
LM
Still Lm is the eigenfunctions. The eigenvalues change. It's L plus times L plus 1, 2i plus G mu B M H bar. Oh, and here I should have put H bar squared. Okay, so mathematically it's not more complicated. Physically, I checked if you understand what are the axes and things that are connected. Okay, now I have two paths that I can choose. I can ask myself, can you develop your let's say, an understanding of time dependence? No time, what do you want from me? So, I'm coming and telling you a time T correct normalization. That's a kosher wave function at time t equals. Okay, when I'm writing the question, I'm debating with myself, does that give too much about the previous two sections, because it actually holds you by the nose and pulls you towards this type of solution? And usually I'm I'm at the end of the day leaning that whoever knows got it, and whoever doesn't know, it won't help him, which usually works for me. Okay, so I'm asking, what's the question? Let's say,
How you can write it without show it's look like the LM if you don't want to.
I could have written being real, it's not really crude, but crueler than this thing. Just writing down the explicit wave function in theta and phi would upgrade the difficulty of this problem.
How it's looking. Just there with the.
Okay, the 0 is 1 over 4 pi.
It's the harmonical.
Yeah, so that's that, and the second guy would be phi is equal 0. I don't remember.
Just writing the harmonical.
Yeah, I could be. It makes it harder. Perhaps if the other question is somewhat easy to my taste, I'll go in that direction. Maybe not. Maybe I'll be mistaken and think it's not so hard and it's harder than it happens. Okay, so I write this thing. What do I expect you here to do? Let's can write down the Schrödinger equation and break my back here trying to solve it, but that's all I need here.
Just the time.
If I understand that if I have an expansion of the wave function in the eigenvectors of the energy, all that is added is a phase corresponding to the energy, and we emphasized it at least twice during the course.
And the truth is that you have already solved your Schrödinger equation.
Because that's eigenfunctions. All I have to do is pull out from the previous question that
eigenvalues of the Hamiltonian.
ELM is L times L plus 1 h bar square over 2I plus G mu B N H bar. That's that. Put in the appropriate number, get the phases. Good.
Why would be M?
M, because LZ pulls out
so
M.
It's M the eigenvalue.
M, not the mass, the ones that.
Yes.
Okay. Now I can ask all kinds of questions and see if let's say I want to ask you LZ as function of T average for this stage. Again, I can write down the spherical harmonics, perform the derivatives corresponding to LZ, do the integrals, and with a probability higher than half, get a mistake and go home sad. Or I can use whatever is given me here in a simple way. I just write down Okay, I'll write down already half because it will appear. Remember the minus? That's a check if you remember that quantum mechanics is always in imaginary space, so you have to remember that.
Actually, in the first one it's with a minus, and in the second, in the dual space, is with a plus.
It doesn't matter how you choose it. Zero. And 0 plus 5, 8, 0, 0, t, bar, 0, 0. Okay.
That's zero.
It's 0 because all the ends.
So I'm looking on it. And LZ here will pull out a 0. LZ here will pull out a 0. And it's 0. Finish. And to get it from directly differentiated and integrating sines and cosine, I'm more doubtful that you'll get it. But if you went down this route, you didn't internalize a lot of what we tried to give in this course.
Actually, you can even see it from the start because.
And the better answer is LZ. This and this is both eigenfunctions of LZ, and therefore nothing changes it, so it has to be 0 and not dependent on time. Now, if I'm only limited to 2 questions, not 3, so I'll give here something that is a bit more interesting, but it's the same way of solving it. How would I do it? This I would call it is a section of this question that differentiate the 90% student from the 100% student. How do I do that? Again, I could do brute force. Here I don't believe that anyone.
Since you know LZ, you know nothing about LZ.
Right, but I have here some superpositions that I'm not so sure that I don't know anything. If it would have been just one of them.
Because there is 0. No.
You're not so sure what's LX, LY. Okay, so the whole game is realizing never leave the spaces, because any time you leave the spaces, you're setting yourself into trouble. So what can you do here? And then hopefully you remember or see in what's written, as I said, the material is open. There were two other operators that we played there in addition to Lx and Ly. L minus and L minus. So L plus was Lx plus I Ly, and L minus was Lx minus I y Ly. So adding them is equivalent to Lx. So I'm putting here L, instead of doing the calculation with Lz, for the case that I'm looking on Lx, so it will be all of this the same, all of this the same, and here I'll write L plus plus L minus.
Divide by 2.
And I'll divide by 2. And whoever forgets to divide by 2, that's not a cardinal mistake. Okay, and this I know what to do with it. Up to the normalization constant. So on this guy, nothing can happen, because if you're stuck at 0, end of story. And the other thing that you have learned here, on 0 plus or minus will push you to m plus m minus. You'll have here m plus m minus. And you'll have only the combinations of them that are equal here. So you do the multiplication, get the result, and that's the result. Now, that's one route that I could go down. The other route that I could go down is asking myself the following. Put in a section. Tell me which one of the following operators could be Hamiltonian. Only one of them could be Hamiltonian.
The short one.
The last one. This is not Hermitian. This is not Hermitian. This is Lx plus I Ly. And this is Hermitian, this is Hermitian, but this is not. With the minus the same guy. Here I'm reminding with an I before everything, and that can't be Hamiltonian. Only this one works. So it checks if you remember what is a Hermitian operator and what the end that I can't get imaginary answer to them. So, yeah. So this is one thing that I can go that, like taking some physical problems that is connected to something you saw first and do. Other route I can go and say, well, I have the complete freedom to build a Hilbert space and operators, whatever I imagine. Right? The rules of the game are the same. Okay, so I come and say, well, yeah, I'm telling you I have a D equals 3 Hilbert space. I come and ask you, give me a basis. Now, on the one hand, it's the easiest question that you would ever be asked. But people who don't grasp exactly what the games that we're playing here could run into problems. Right? What do I diagonalize here to get the eigenfunction? That's the basis. I didn't say what basis. And so you come and write down the canonic base. Answered it. Did it require any mathematical work? No. All it did is that if you know nothing, you have the canonical basis. Go forward with it. Now I come and ask you, I have this Hamiltonian. Okay, what are the eigenvalues and eigenfunction? So in order that you have units of energy, I write E0 before it.
The first one is an eigenvector.
So, and again, 3 by 3 is still simple enough to solve it brute force, but why? One of the most important things about matrices is to identify blocks. If you have blocks, life is good. What is a block? A part of the matrix that has only zeros to both of its sides. So, one I immediately identify. So I'm writing down. And this type of 2 by 2 block you should know by heart. What is the solution of it?
1 minus 1 times 1 over squared.
It's the x operate. It's the x operate.
Finish. I see people going and doing the brute force, hopefully without doing mistakes on the way. It's not much more complicated to write down here. I'm writing down the determinant. And actually, you should have shot me because that's a minus.
I do understand the eigen, the less to eigen. Don't understand it. Only for loop, the block.
I don't need the normalization here. Okay? That's what's happening here. Right, the Hamiltonian times this part. This times this is -1. This times this is 1. This is exactly minus of the original one. What's minus? Finished. Now, what will happen if you have here 2 and 2?
And the diagonal addition.
Multiply.
No, you don't.
You divide to normalize the.
So now I could ask a question. What is it? Now I can play. Okay, I wanted to finish that, which was good that I checked here. It's -1 lambda plus 1 lambda -1. So I immediately see two values of 1 value of -1, which we have seen previously. Okay, now can start doing physics here. Until here, mathematics, not complicated, but as a teacher, with enough steps that people can miss something. Look, diagonalizing 2 by 2 matrix, physics graduate should be able to do. So even if he's not seeing this structure. Now, here I can do interesting physics. Why, for example? Because I have degeneracies. Okay, if I tell you what is the eigenvalue if I measure minus is 0?
It's the eigenvalue or the eigenvector.
Yes, so I can come to you and say, well, I have the following wave function. What is the probability of measuring minus E0?
Minus E.
Yeah.
And it, zero. No probability to get it. Because we can create this from adding this, and this is not a
So if I want to be rigorous, I use what we have studied. Probability of measuring minus E0 is the eigenvalue for measuring E0, sorry, the eigenvector for times the wave function that you gave us. So here I had 1 over square root of 2 and times 1 over square root of 3. I gave. You multiply, you get 0. Very nice. If I ask what is the probability of measuring E0, I could go and multiply this, or I could be a bit cleverer and say, I know that you can't measure E0, minus E0, so it has to be 1. And you see how on and on I can play games here. Let's say I tell you I measure E0, what was the collapse of the wave function?
The probability to find minus E0 is 1.
It's already in that space.
It's already in that space. Nothing happens. There's no collapse. Because I didn't measure anything useful. I knew before the measurement that the probability is 1, and after the measurement that the probability is 1. Now I can play with a different, put in time, you see, endless games, and all I did is build a Hilbert space, define some operator, and went on with games about it. Can define, find here some operators that will be commutes with it and stays with the same. Everything is open here. So there's enough of space to create your new questions with no new materials.
In general, if you make a measurement and the thing you're measuring has more than one dimension, so like E0 had 2 dimensions, so you had 2 vectors. Then you project onto the subspace of it.
So if you had your 4 values and you went down to 3 values, not really complicated to do, but harder. But in this case, it was trivial, just checking your understanding. In general, these are the type of questions. It could be a system you never heard of. It's operators you have never seen, but at the end of the day, it's the rules that you know, the procedures that you have met, and you're supposed to just go through and know the definitions, what you're trying to measure, what are the eigenfunctions of the operator you're looking at, what does measurement do, how the wave function develops with time, how any measurable operator evolves with time, and all that you have proves that this operator and that operator have the same basis. Of course, commute and see. So on. Clear thinking, precise writing down the rules. That's it. Not get scared if you see some operator you have seen before. Okay, any other questions?
I have one actually. It's about something that was in the homework a few weeks ago.
Okay.
If you have 2 operators that commute, then they have the same eigenstates, right? But in one of the questions, one of the operators was represented by the identity matrix, and another operator was, I think it's the one that actually wrote them down. The identity matrix.
You see, even
because it's always the same. Right? So the identity matrix, it commutes with everything, but the eigenstates, they're not exactly the same. Because everything is an eigenstate of the identity. Something degenerate happens in this. So, how does that?
Okay, so actually, the second part of the course, undergraduate quantum mechanics 2, degenerate subspaces will play an important role because of perturbation theory. You have to put in some corrections to the standard perturbation theory in order that it will work in this degenerate subspace. But okay, let's go and try to understand what's happening here. And okay, so I have my Hamiltonian, have the identity matrix. Of course, it's a no-brainer that H commutes with I. So it's 0. So both of them are can have the same basis, right? Then you stop and look. This guy can have as a basis, well, this is natural, but any other combination, right?
Linear independent combination.
Correct. This guy has to have a specific combination. Both have to have the same, can have the same basis. I didn't say that every basis that belongs to one belongs to the other and vice versa. It's possible to create a basis that is a basis of both operators. So this base is good for this, but not good for this.
I see. So if two operators commute, then there exists a basis.
Right. I didn't say that each basis of one of them is also the basis of the other. As you say, I can prove that it can't be correct. I is any linear combination, and if it commutes with any operator.
And any non-diagonal operator has up to normalization on a unique basis, so therefore you can always say that there is no identity or diagonal matrix there. There's a unique solution to the problem.
All right. Because here there is a unique solution, here there's not. So the space of solutions here is larger, and I only say there exists a basis that belongs.
And this case can happen. It doesn't have to be the identity matrix. Right?
No, it could be
anything with degeneracy.
Anything with degeneracy. You're already you have to be careful. Check which. The fact that it works for one doesn't necessarily. Look, we did exactly such an example. Look, we took, let's say, the parity operator and the Hamiltonian, let's say, of a particle in a harmonic oscillator. They commute? Yes, the problem is symmetric around 0. It has the same potential energy. Pi is all the eigenvalue, the eigenvectors of pi are all the odd and even functions. Is any odd and even function a solution of H? No, we had to work hard to find out what are the solutions of a harmonic oscillator, right? So this has a much larger possibility of building bases than this guy. Nevertheless, there is a base that has a defined parity, which is the solutions of the harmonic oscillator, and are also eigenvectors of the parity, not vice versa. Not any basis of the parity or any odd or even function is necessarily a solution of the harmonic oscillator. You know that. Same thing. More questions? So good luck with the exam. If you have questions, send me an email. If I see that there is a whole bunch of questions, I can arrange a meeting for the exam. If it's one or two, we'll either set a private meeting or do it by Zoom. We'll see what's more convenient. Okay.
נגיד סתם דוגמה, אמרנו שזה היה